Hi guys, I would wish to take you through Form 3 first topic, that is in the KCSE, that is a syllabus. And therefore, our first topic is data representation in a computer. And to start with, we shall look at the course outline. And therefore, in our course outline, we have introduction, we have data representation in digital computers, magnetic media, and optical media. Then we have reasons for use of binary system in computers. We shall also look at the terminologies bits, bytes, nibble, and word. We shall also look at types of data representation, then number systems, also binary arithmetic operations. That is, we shall do addition and subtraction. To start with, computers handle data by electrical components. That is, for example, transistors, semiconductors, integrated circuits, or cables or wires, which exist in two conditions. Therefore, a computer operates in two conditions of on and off, or toggling. That means it is either in a state of a 1, that is on, or a state of off, which is 0. Therefore, 0 off, 1 on. Inside the computer, data is represented by storage cells. We call them arrays or variables, which are either electronically charged or discharged. Examples: in random access memory or RAM, the cells can be charged and discharged at will, and this can be used to store different data items. The charged state of the cell can be represented by a 1, that is on, where the uncharged state by 0 or off. In read-only memory, that is ROM, the cells are permanently set to one state. Then a transistor may be conducting or non-conducting, that is conducting or non-conducting. A magnetic material may be magnetized in one direction or the other. A wire may or may not be carrying a current. The memory of a computer can be considered as a collection of thousands of storage cells, each capable of representing a binary digit. Therefore, that is our introduction on what you need actually to visualize in your mind before we go on our topic, that is data representation in digital computers. It is also important for us to look at data and data types so that at least you can have a clue on what we shall be covering. When you talk about data, data is a term used to describe a set of facts. A single fact is known as datum. Data can be in three types or forms. We can have numeric data, that is numbers 0 to 9. We can also have alphabetic data, A to Z, also including the special characters, the wildcards. Also, we have alphanumeric, that is a mixture of numbers and alphabets. For instance, you can look at the car number plate. It is a mixture of numbers and alphabets. Then we can also try to look at numbers. Numbers can be expressed as either integers, that is whole numbers, real numbers, that is with decimal points. Then we can also look at alphabet numbers. Therefore, we have something like this data made from combination of alphabetic characters such as names, titles, marital status. Then you can also talk of alphanumeric data or strings. In programming, they are called strings. A string is a sequence of characters. This is data made from combination of alphabetic characters, numerals, and special characters. For example, you can look at, we have name, address, date, account number. The example I have given down there. Then we can also visualize on data signals. When you talk about a data signal, it is the flow of current that is through the transmission media. Data is carried in terms of current. And therefore, in digital computers, the user inputs is converted and transmitted as electrical pulses that can be represented by the two digits, a 1 and a 0, that is 1 and 0, before processing. These two digits are referred to as binary digits. Therefore, from today henceforth, when you talk about a 1 and a 0, that is in data representation, we call it binary. Therefore, the word digital, like now in other terminologies, we had dicotyledon, di means to, digit, that is digital, means to, binary, by, to. Therefore, binary and digital means we are in the state of a 1 and a 0. And therefore, we have digital signal. We also have analog signal. Therefore, a digital signal is non-continuous or non-discrete, whereas an analog signal is continuous in nature. Therefore, you can see the two, that is the two diagrams here, the analog signal, therefore it is continuous. Then we have this one that is breaking, that is the digital signal. Then let's look at how data is sent through a telephone line. This is very crucial. It's very important in our topic because we are dealing with data representation. Therefore, we also need to see how data is transmitted. Therefore, when a digital signal is to be sent over an analog telephone line, for example, an email, it has to be converted to analog signal. This is done by connecting a device called a modem. And therefore, the word modem is an acronym for modulation, demodulation, modem. Therefore, this is done by connecting a device called modem to the digital computer. This process of converting a digital signal to an analog signal is known as modulation. On the receiving end, the incoming analog signal is converted back to digital form in a process known as demodulation. And that's where now we usually get the term modem, modulation, demodulation. Let's look at the diagrammatic representation of modulation and demodulation. And therefore, if you look at this one, this is the sending computer. On the other hand, we have the receiving computer. And then a computer processes digital data. But a telephone line must transmit analog signal or analog data. And therefore, the computer, between the computer and the telephone line, we must have a gadget called modem. And also on the other end, that is the receiving end, from the telephone back to computer so that somebody can read the email, we also need another gadget called a modem. And therefore, the process of now, this one is modulation, whereas the other one here is demodulation. Therefore, this is what happens. The sending computer sends digital data to a modem converts it from digital to analog, that is modulation. Then it is transmitted. On the receiving end, another gadget, another modem of the same kind, takes the analog signal and converts it back to digital for readability, that is demodulation. And therefore, that's the work of a modem. Then we can look at concepts of data representation in digital computers. Data and instructions cannot be entered and processed directly into computers using human language. Any type of data entered must first be converted into machine-readable form, that is binary form. Computer, together with its peripheral devices, handle data in its electronic circuits, magnetic media, and in its optical devices. And therefore, we shall look at data representation in electronic circuits. Back in Form 1 physics, you have learned about circuits. And therefore, if you look at this diagram here, it is actually showing you that the bulb is lighting, and therefore that is to show you that there is a flow of current. On the other hand, the bulb is off, showing you that the circuit is disconnected, and therefore there is no electric current. Therefore, this is a very good representation or a demonstration of how computer works. It works in a state of on and off. And therefore, electronic components such as microprocessor or the computer brain are made up of millions of electronic circuits. Availability of a high voltage, that is on, in this circuit is interpreted as 1. Therefore, availability of current flowing, like in diagram 1, is interpreted as 1, where a low voltage or off is interpreted as 0. Simply, that's how you can explain how electronic circuits represent data. Then we can look at data representation on magnetic media, and therefore we have a demonstration here of poles, that is the south and north poles. We have repulsion and attraction, that is in the principles of magnetism, still in Form 1 physics. The presence of a magnetic field in one direction on magnetic media is interpreted as 1, while the absence of magnetic field is interpreted as 0. Therefore, basically, if you are told to explain how magnetic media represent data, or how data representation of magnetic media works, just explain that the presence of magnetic field flowing in a certain direction is indicated as 1, whereas the absence is indicated as 0. Remember, our topic is digital, that is data representation in digital computers, and therefore you're talking of binary or digital data, that is a 1 and a 0. That is our point of focus. Then, how does a CD write out, that is write and read data? Remember, the process of writing a CD is commonly known as burning, that is burning a CD. And therefore, if you look at the reading of data or data representation in an optical media, a CD is an optical media. We talk of laser beam. And therefore, in diagram number 1, we have a smooth recording surface. Then we have very concentrated light. We call it laser beam, that is reflected on the surface. Then, on the other hand, laser beam is not reflected. That is in the other figure, showing you that whenever there is laser beam, it actually make the flat surface to form rods and pins where zeros and ones, that is the binary data, can be dropped for storage. And therefore, when we talk about a CD writing data, we use a concentrated light called laser beam that is passed over a flat surface and forms pits and rods. Then another layer comes on carrying zeros and ones and dropping them on the on those points, forming data storage. Then we also need to look at the terminologies used in data representation in computers, and therefore we shall first of all try to define the word byte. The capacity of a computer memory can be measured in terms of bits, that is individual memory cells. Then bytes, group of cells or bits. Then we have word, arrangement of bytes. Therefore, let's look at them one by one. Terminologies used in data representation: we have a byte, we have a bit, we have a word, and we have a nibble. And therefore, when you talk about a bit is a single character, whereas a byte is a combination of 8 bits. When you have 8 bits, then you have a byte. Then you have a word. A word is a group of bits that the computer recognizes and executes, that is processes at a time. Then a half word is called a nibble. Therefore, you can just say that a half word or a half byte, that is 4 bits, is referred to as a nibble. Then you can also review Form 1 work so that you can see this part of bits and how they are converted to megabytes, to gigabytes, and to terabytes. Therefore, review Form 1 topic, computer systems. I have also done a video on that. You can just get it in the description below this video. Then we can look at coding of data. A computer can understand only one language consisting of 2 symbols, 1 and a 0. That means for you to key in anything in the computer, it is converted into this one language of a 1 and a 0, that is binary digits. Since the computer cannot understand data represented in human languages like 0 to 9, A to Z, special characters, it became necessary to change the data to binary form through a process called coding of data. And therefore, coding of data is changing the human readable data to machine readable form, that is binary form. In other words, to make communication possible between computer and human beings, data must be coded in the form that can be understood by the computer, and the information supplied by a computer after processing must be coded in the form that can be understood by the user. The coding and decoding of data in a computer is done by the input-output devices. Therefore, you can now have the clue on what is coding of data. It is actually converting data to machine-readable form. Therefore, codes used in computer systems, therefore you can look at whatever happens. We have a human message, then the computer works in the CPU code, then the human readable or machine readable code is actually now given to the machine for processing. Then we also need to know something still on this topic, on this subtopic, coding. We have symbolic representation using coding schemes. Remember, we have said coding is converting of human readable to machine readable, that is binary form. In computing, a single character, a letter, a number, or a symbol is represented by a group of bits. This is called coding schemes. We have the following types of coding schemes. Therefore, we have the binary coded decimal. It is abbreviated as BCD, that is binary coded decimal. We have extended binary coded decimal interchange code, or EBCDIC. We also have the ASCII, or American Standard Code for Information Interchange. Therefore, make sure you know we have the BCD, we have the BCDIC, and we have the ASCII or ASCII. Then we can look at a brief description of each. Binary coded decimal or BCD. It is a 4-bit code used to represent numeric data only. For example, a number like 3 can be represented using a binary coded decimal as 0011. Later on in this topic, I will be showing you how to convert numbers to binary. Then BCD is mostly used in simple electronic devices like calculators. Therefore, BCD is a coding scheme that uses 4 bits and is only used to represent numeric data. Then we have the extended binary coded decimal interchange code, or EBCDIC. It is an 8-bit character coding scheme used in IBM computers. A total of 256, that is 2 raised to power 8 characters, can be coded using this scheme. Then we have the American Standard Code for Information Interchange, ASCII. ASCII, as it is read, is a 7-bit code, which means that only 128 characters can be represented. There is an 8th bit to this code scheme, which can provide for 256 characters. The 8th bit coding scheme is referred to as 9-bit ASCII. For example, letter A is represented as 10000001. That 2 there, we shall look at it, what it means. It actually means binary. It is base for 1 and 0. Then we can go ahead now and go to a very interesting part of this topic, that is number systems. The design and organization of a computer depends on the number system. The 4 number systems are, we have binary number system, we have octal number system, we also have decimal number system, and lastly we have hexadecimal number system. Therefore, we shall go one on one, and then we shall understand what we mean. Let's start with the decimal number system. The decimal number system is also called the denary number system or base 10. Many people call it base 10. The decimal number system consists of 10 digits, 0 to 9. I'm sure you are wondering how they become 10. If you count 0 to 9, remember 0 is a number, you are likely to get 10. You will actually get 10. And therefore, decimal number system consists of 10 digits, 0 to 9. In decimal number system, each digit has a digit value, 0 to 9, and a positional value, which is determined by how many places to the left or right or to the right of the decimal point the digit is written. Note, the digit value and the positional value for each number system depend on the base of the number system. Powers of base increase as we move to the left and decrease as we move to the right. That is a very important point. Therefore, let's look at what I am actually talking about. Right now, we have the position. We have first or up to 7, for example. Then we have power base. Then we have the value. Like for instance, if you look at the first value there, we have 10. Therefore, we start from our right hand side towards our left hand side, and therefore we start from power 0, power 1. Powers increase as we move to the left, and powers decrease as we move to the right. Remember that point. We shall be doing some calculations, and therefore you will be in a position to understand more. Then we have the binary number system. Binary is the representation of data by only two possible conditions, that is a 1 and a 0. That is combinations of 1 and 0. Binary system is a number system that uses only two digits, 0 and 1. It has a base of 2 and is therefore called base 2 system. Now, if you go back a bit on the decimal number system, it has a base of 10. That's why we call it base 10. Whereas binary has a base 2, that is base 2 number system. In binary number system, the digits 1 and 0 are referred to as bits or binary digits. For instance, look at this number. We have the exponential value, and then we have the integer value. And like for example, let's start from our right hand side. We have 2 raised power 0, 2 raised power 1. Therefore, powers increase as you move to the left. And therefore, any number, and when you talk about that is 2 raised power 0, 2 raised power 1, 2 raised power 2, down there we have the values that indicate them. And therefore, we have 4, we have 8, we have 16, that is 2 raised to power that number to get the value that is below there. Then we have the octal. Octal means 8. Octal number system. In octal number system, there are only 8 possible digits, 0 to 7. Each digit or number is base 8, is in base 8, has its value, its place value determined by 8. The position value of a digit increases to the left of the octal point in ascending powers of 8. For example, 2163, that 8, base 8 there, shows that it is octal. If I put 2, it means binary. If I put 10, it means decimal number system. And therefore, this number here, 2163, with the base 8, which is indicating it is octal, it can be represented as follows. Therefore, you assign the power to base 8. Therefore, we start by 8 to power 0, 8 to power 1, 8 to power 2, 8 to power 3. Remember, we have said that once you write the base, like when you write 10, that is for base 10. When you write 2, that is for base 2. When you write 8, that is for octal. The powers increase from right to left. Make sure that one is well understood. Then we have the hexa. Hexa means 16. Hexadecimal number system. Hexa means 16. In hexadecimal number system, the base is 16, and therefore, there must be 16 digits. The 16 symbols used used in hexadecimal number systems are 0 to 9 and alphabets A to F. Therefore, we start from 0 all the way to 9. Then when we reach number 10, look at the description below. 10 becomes A, 11 becomes B, 12 becomes C, 13 becomes D, 14 becomes E, and 15 becomes F. Therefore, you shall be in a position to see that when doing calculations. Therefore, for example, look at this. We have assigned, we want to represent 12A0. Each digit in the hex number system has its place value expressed in terms of 16. For example, the value 12A0 can be represented as follows. Therefore, you assign the powers to be 16. You start by, you write the number the way I have written it. Therefore, you see what I have done. We have written 12A0. Then you write 16 from the right hand side towards the left hand side. Then you start 16 raised to power 0, 16 raised to power 1, and the powers increases until you get the last digit. And therefore, for that matter, this one is now well represented. 16 to power 0 represents this that way. Then let's look at the mathematical part of it. Be prepared. We are now doing the conversions. Therefore, base conversions. Human beings normally work with the base 10 notation. That is, all the data passed to go as computer input is usually in decimal notation. Subsequently, the results of the computer operations are communicated to the user in a form they can understand, that is in base 10. The base conversion is therefore used to help computer users understand how data and information is communicated between the computer and the user. Therefore, let's start by looking at how do we convert decimal to binary. Remember, we have said decimal is a number with base 10, whereas binary is a number with base 2. And therefore, our first activity is to convert decimal number to binary. To convert a decimal number that is base 10 to binary number that is base 2, the decimal number is repeatedly divided by 2 until the number cannot be further divided by 2. On each division, the remainder is noted. Then, the remainders are copied from the bottom upwards to give the binary equivalent of the decimal number. For example, convert a decimal number 121, therefore it has a base 10, that is meant to tell you it is a decimal number, to binary. Therefore, what you need to note, you divide the number continuously with 2. If it is divisible by 2, you write 0. If it is not divisible by 2, you write 1. For example, 121 divided by 2, you get 60 because of 120. Therefore, it is not divisible by 2. Therefore, you write 1. Then you get 60. 60 divided by 2, it is divisible. You write 0. You get 30. 30 divided by 2, it is divisible by 2. You write 0. You get 15. Is 15 divided, when 15 is divided by 2, you get 7, but 15 is not divisible by 2. That is, it is not completely divisible by 2. Therefore, you write 1. Then 7 is also not completely divisible by 2. Therefore, you write 1. 3 is also not completely divisible by 2. You write 1. Then, at this point, you get that this one, that is 2 divided by this one, you get actually a fraction. Therefore, you write 1, and that is you write another one here, and therefore that is the end of the end of the the calculation. Then from there you draw this arrow, that is to show the person reading that you are reading these values from bottom to top, and therefore you write 1 1 1 1 0 0 that way. Then this one at the rows, and then you give a base 2. Because we have said representation of ones and zeros falls under base 2. That is a binary number system. And therefore, this is how you have now come to know that the answer is this one. Then we have example 2. Convert the following decimal integers into binary equivalents. We have 36. Therefore, 36 divided by 2, it is completely divisible. Therefore, you write 0, you get 18. 18 is completely divisible by 2. Therefore, you write 0, then you get 9. Now, 9 divided by 2, it is actually the nearest is 4 because of 8. It is not completely divisible, and therefore you write 1 because of 4. Then 4 divided by 2, it is completely divisible. Therefore, you write 0 and you get 2. 2 is also completely divisible by 2. You write 0, then limit 1. Then you read from bottom to top. This is the most significant bit to the least significant bit. Then you write that one as the answer. Therefore, that's how you convert decimal to binary. Then you can also look at this example of whereby we are converting 247. Therefore, you divide by 2, you get 123 because of 246. But since this one is not completely divisible, you write limit 1. Then you divide 123 by 2. It's also because it will actually be 161 because of 122. Because it is not completely divisible, you write 1. But when you get a value is completely divisible by 2, you write 0. And the story now repeats itself. That is the wrong method of doing that. Then sometimes you can get a fractional number like 26.25, and it is in base 10. Therefore, for a fractional number, the number is divided into two parts, the whole number part and the fractional part. That is the integral and the fractional part. The whole number is then converted to binary individually as shown above. The fraction part is repeatedly multiplied by 2, noting the complete units of 2. This is done until the fraction becomes a 0 or start recurring. The complete units of the fractional part are then copied downwards. Therefore, let's look at that. If you are given an example like convert a decimal number such as 26.25, you subdivide the number into 2 like I have done. Therefore, this is 26 on its own, then the fractional part 0.25 on its own. Therefore, you separate the first part, and you also separate the second part. Then the first part, that is the first part, that is the whole number part or integral part, you continuously divide by 2, like I have taken you through in the other example. Whereas the other part, you continuously multiply by 2. Like for example, 0.25 times 2, you get 0.50. Therefore, you only write this part. You write this part. Then, like for example, now you write 0 for this one. Then you take now the decimal part, that is 0.50 times 2, you now get a 1. And therefore you have said that you stop calculating when it starts reoccurring or when this becomes 1 or 0. Therefore, for instance here, this one has actually become 1, and therefore you don't need to continue again taking 0 times 0 because this is actually 0. Therefore, you cannot take 0 times 2 because you still get 0. Therefore, once it becomes 0, you just stop it at that. Therefore, it is not necessarily hence you stop. And therefore, for the fractional part, you read them downwards, but for the integral or the whole number part, you read them going upwards. And therefore, you just now combine the answers. You take this answer, get here, you combine with this one, separated with the decimal, the way it was. And therefore, the answer is this one. Therefore, for fractional part, first of all, you separate the two parts. That is the first thing to do. Then you calculate them separately. Then we have the fractional. That is, we go to the next part 2. Let's see how do you convert binary to decimal. Remember, binary is in base 2, decimal is in base 10. To convert a binary number to decimal, the number in binary form is assigned weighting factors, place values for each digit. The partial products, that is the product of each digit and its corresponding weight, are obtained and then added to give a decimal number equivalent of the binary number system. Example, now look at how I'm explaining this. Convert the binary number, this one. Remember, a binary number must be a combination of ones and zeros, to decimal. Therefore, the first thing, you arrange these numbers down. Look at how I have arranged them. You arrange them into the way it is. Then you can draw this line. Then above it, write is 2 equivalent. That is, for every number you write a 2. For every number you write a 2. For every number a 2. Another one a 2. Another one a 2. Then the second thing, you start from your right hand side, assigning the that is the power of. Therefore, here we start from 0. The powers goes increasing to 1, 2, 3. Then from there, you will now go to using indices. Any number raised to power 0 is actually 1. Any power raised to power 0 here should be actually 1. And therefore, this one should be 1 times 0, 0. That is just to say 2 times 0. Then any number raised to power 1 is itself. And therefore, this is 2 times 1. You get 2. This is any number raised to power 2 is that number times that number. Therefore, this is 4. 4 times 1. This is 2 times 2 times 2. This is 8. 8 times 0. You get 0. Then this one is 2 times 2 times 2 times 2. That is actually 16. And therefore, that's what has been done here. That is equals to 1 times 2 raised to power 4. Then 0. That is 0, this one, 0 times 2 to power 3, then 1, this is 1 times 2 to power 2, then 1 times 2 to power 1, then the last one, 0 times 2 to power, then you add them up. And therefore, this number here equals to 22. And therefore, if you take 22 and divide by 2 continuously, the way I have taken you through the other one, you'll get this answer. Therefore, let's look at the explanation here. Note that the binary number 10 has 5 digits. Starting with the rightmost digit, the most significant digit, that is MSD, is in the 5th position. So it is multiplied by 2 raised to power 4, and each digit on its right will be half of it in its positional value. The products obtained are added together to get the required decimal equivalent. Let's look at example number 2 for more understanding. Convert the binary number 11,11001. That small 2 there indicates it is a binary number system. Therefore, remember what we have said. You draw this schedule, this table-like schedule. Then you write the numbers the way I have written them here. You write the numbers the way they are, all of them. Then you write 2 above each number. Then the next thing you you put the place values starting from 0. That is from the right hand side. The power increases towards the left hand side. Then you multiply them the way you have done here. Now, therefore, you multiply this times this plus this times this plus this plus this times this plus this times this plus this times this plus this times this. Then you get the answer. But once you get the answer, remember to put this unit 10 to show that it is a decimal number. Then, what if now we have the fractional part? What if you are given a number with a fractional part? Like now, convert a binary number such as this one. This one, remember, it has a dot. That is the decimal. Decimal, that is decimal 01. Therefore, what you do, there is not much deal here. You only draw the schedule again, only that where there is decimal, you indicate decimal. Then, from the decimal towards the right hand side, the powers decreases, and therefore you start from raised to power -1, raised to power -2, raised to power -3, raised to power -5, blah, 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 that way. And therefore, the other story remains the same. You multiply this times this plus this times this plus this times this plus that way, that way, that way. Therefore, that's how you go about it. It becomes this plus this one, that way, this plus this plus this. Then you get the answer here. Remember, once you get the answer, you remember to indicate the 10 to show that it is decimal and not binary. This is binary and this is decimal. Therefore, basically what you need to know, points to note, is that you apply the law of indices. Right now, 2 raised to power negative 1 is same as 2 raised to a half. Therefore, you need to have that one in mind. And also this one is equivalent to this. That one, you need to review the law of indices. I think it is Form 2 mathematics. And since you are in Form 3, you are supposed to have taken indices so that you can be in a position to apply the law of indices here. Therefore, basically, there is not much deal on that, only that the powers decrease towards the right and increases towards the left. Then we can look at how do we convert now decimal to octal? How do we convert decimal numbers to octal? That means to base 8. To convert a decimal number to its octal equivalent, divide the number given repeatedly by 8 until the quotient is the answer you get when you divide, obtained is 0. Therefore, don't forget that if I tell you convert for me 691 to octal, look at what I have done here. You continuously divide the number, but this time round, you actually write the actual remainder. And therefore, 8 divided by 691, you get 86 because of 3. Then you write the remainder. That's the remainder on the number that is equivalent to that one. Then you can actually now follow that example there to get that on how that one is actually done. You can also look at this example here. Therefore, you can also practice because I've actually solved it. Then we can look at the fractional numbers. When you have a number like 98.12510, therefore this one is a replica of what we did in binary. You separate the two parts. The first part you continuously divide by 8 and write the remainders, whereas the other part you multiply by 8. That is the fractional part, just like we did in the other one. Then you write the numbers just like we did on the other one. Right now here we have gotten 1, and therefore since this part is 0, 0, you leave it at that and then take that number. Therefore, you also have another example here solved. Then we can also look at octal to decimal. When that is to revert. When you are converting octal to decimal, you actually assign the weights. Like now, you draw this schedule. You write the number. Like for example, convert 1263. This shows you that it is octal to decimal. Therefore, you write just like we did in binary. That is decimal back to binary and vice versa. Therefore, you write the number 1, 2, 6, 3. Then above it, you write 8, 8, 8. Then from your right hand side towards the left hand side, you start from power 0, power 1. Then you multiply. This times this plus this times this plus this times this plus this times this. Then you will get the answer. Therefore, basically, you can practice on the others since all of them I have solved. Therefore, basically, that's how you just go about it. Then when you have the fractional part, you just do as we have done in binary, only that now from the decimal part towards the left hand side, the powers decreases. Therefore, it becomes 8 raised to power negative 1, 8 raised to power negative 2, 8 raised to power negative 3. Then the other story remains that it is this times so this plus this times this plus this times this. Therefore, the other part remains. But when you are adding up, the decimal part, you add it separately, and then you also add the integral or the whole number part separately. Then you bring the answers together, just like that one has been solved. Then we have the rusty part on number systems. We have the decimal to hexadecimal. Therefore, the decimal number is repeated divided by 16, where when you are noting down the remainders, just like I have actually demonstrated here. Therefore, you just divide like now, convert 122. This 10 means it's decimal to hexadecimal. You just divide by 16 as you write down the decimal. But remember, when you get 10, I have taken you through that 10 is A, and therefore you have 10, 11 up to 15. Then you write A, B, C, D, E, F. Therefore, like now for this one, convert this one, we got 10, remainder 10. Therefore, 10 is, you don't write 10, you write A. Remember, A, B, C, D up to E to F. Then convert decimal number 745 to this. Therefore, after dividing, there is somewhere we got 14 as remainder. And therefore, 14, you write letter E. You don't write the 14, you write the letter. Therefore, practice much on that one. Then when you get decimal part, the same story repeats itself. The integral part you divide by 16, whereas the fractional part you multiply by 16. Then for you to convert hexadecimal to decimal, the same story again repeats itself. Like now, convert 7A to decimal. You write 7A. Then above A, you write 16 to power 0, 16 to power 1. The numbers increases as you go to your right and decreases, as you go to your left and decreases as you go to your right. Therefore, you can follow the solved examples here so that you can be in a position actually to get it right. Then from there, you can look at how we convert binary to octal. Like given an example, to convert binary to octal, you just arrange them in terms of, let's go straight to this example. Okay, how do you convert octal to binary? Like now, convert 347 to binary. Therefore, the first step, convert the given number to base 10. I have taken you through how to do that. You just write the number 347. Above it, you write 8 to power 0, 8 to power 1, 10. Now, once you get the decimal part, that is step number 2, then convert the resulting decimal number to binary. I have also taken you through that. Therefore, to convert, you first of all take it to decimal, then you take it to binary. Therefore, you can later on look at those examples. Let's also go to a different subtopic, that is negative numbers. How does a computer, or how do computers convert or deal with the negative numbers? Now, both positive and negative numbers can be represented in computer memory during processing. The input numbers, whether positive or negative, are all represented in binary form. The negative numbers are used to carry out subtraction in computers' arithmetic operations. This is based on the fact that subtracting a number is the same as adding its negative to the number. The following are the various methods used to represent negative numbers in computer. Therefore, in an exam situation, if you are asked to name how computers represent sign bits or negative numbers, you will give these 3 methods. Number 1 is 1's complement method. Number 2 is 2's complement method. Number 3 is signed magnitude method. Therefore, those are the 3 methods used to represent negative numbers. Therefore, let's go one on one. Let's start with 1's complement or 1C. Now, in 1's complement, the binary digits representing the negative numbers are negated. To negate means that whatever was a 1 becomes 0, and whatever was 0 becomes 1. That is, the ones in the number are changed to zeros, and the zeros are changed to ones. For example, negative 17 can be represented in binary as a negative value as follows. Therefore, I have taken you through how to convert a decimal number. Whenever you see a number with base 10, that is decimal, and therefore this is a decimal negative number here. You want to convert it to binary. Therefore, we have said you continuously divide by 2. And if the number is completely divisible by 2, you write a 0. If it's not completely divisible by 2, you write remainder 1. And therefore, our answer is 10001. And therefore our number here, in this case, the answer you get there, you negate. Whatever is 1 becomes 0, and whatever is 0 becomes 1. Therefore, look at what has been done here. Therefore, a 1 becomes 0, a 0 becomes a 1, a 0 becomes a 1, a 0 becomes a 1 becomes a 0, and therefore the answer is this one. Therefore, in one's complement, if you are told one's complement of a number is the bitwise not, or it is the negation, it is the exchange of zeros and ones. Whatever was a 1 becomes a 0. Whatever was a 0 becomes a 1, just like it has been described here. Therefore, this is 17, and therefore, to show that it is a negative number, you negate. This becomes 0, this becomes 1, 1, 1, 0, and therefore the answer becomes this one. That is in one's complement. Then, 2's complement of a number is 1's complement of a number plus 1. As simple as that. And therefore, the answer we got in our last calculation up there, we are only supposed to add 1, and then we get the answer. And then in case you get an extra digit that is not required, we call it an overflow. If you want 4 digits and then you get 5, the fifth digit there will be termed as overflow. If you want 8, then you get 9. The 9th digit is called an overflow. And in 1's complement, we add the overflow to the answer. In 2's complement, we ignore the overflow. And therefore, the 2's complement of a number is 1's complement of a number plus 1. Then we have signed magnitude method. In signed magnitude method, the number is divided into 2 parts, the sign part and the data part. Usually, a 1 is used to represent a negative sign and a 0 to represent a positive sign. The magnitude part is expressed in binary but not complemented. Therefore, one part of the binary digits will be representing the data value, while the other will represent the sign bit. To make it simple, it is assumed that the sign bit is 1, while the data bits are equivalent to the binary number digits representing 17. For example, negative 17 can be represented in binary as that one, therefore you had divided that, and therefore when it is unsigned, it looks like that. That is 1, 0, 0, 0, 1. And therefore, negative 17, when we add now letter 1, when we add number 1, that is when we add number 1 as shown there, it will indicate that it is actually negative. But if we want to show that it is positive, then we add 0. For instance, if you look at this one, plus 17, I have added 0. This is to show that the number is positive. But for negative 17, there is an addition of 1. Therefore, this is the sign part, this is the data part. This is the sign part, this is the data part. Then from there, let's go to wrapping up our topic. We have the binary arithmetics. Let's see how a computer performs addition in binary and also how subtraction is done. Let's start with addition, that is in binary arithmetics. Now, adding binary numbers is the same as adding decimal numbers. The difference is that any complete unit of 2's are carried and added to the next significant digit. Binary addition rules. We have 0 plus 0, you get 0, and therefore you carry 0. 0 plus 1, you get 1, and therefore you carry 0. 1 plus 0 equals to 1, and therefore you carry 0. But when we write 1 plus 1, we get 10, and therefore we write 0 carry 1. Therefore you carry 1. Therefore 1 plus 1 is 10. That is in binary. Now look at what the example here. 1 plus 1 is 10, and therefore you write 0, you carry 1. Then you add 1 on the other one, it becomes 1. Then when it goes to the other one, it becomes now 1 plus 1. That is, let's do it together. we have 1 plus 1 is 10. Therefore, you write 0 carry 1. You bring the 1 here. And therefore, the 1 becomes 1. Then this one is 0 plus 1, you get 1. This is also 1 plus 0, you get 1. And therefore, the answer remains this one. Therefore, the rule here is that 1 plus 1 is 10. That's why I have written 0 carry 1. And that's what we are doing here. 1 plus 1 is 10. Therefore, 0 carry 1, you bring the 1 here. And drop it here because it becomes 1 plus 0, 1. Then this one remains 0 plus 1, 1. This is 1 plus 0, 0. Then in this case here, 0 plus 0 is 0. 1 plus 1 is 10. Therefore, 0 carry 1. 1 plus 0, 1. Then here, 1 plus 1, 10. 0 carry 1. Then it becomes, you have carried 1. 1 plus 1, 10. And then if you get that answer. Therefore, can you practice on those ones so that you can actually get. And therefore, the explanation is, addition of two binary numbers start from the least significant digits. 0 is added to 0 to get sum of 0. The next significant digit 1 and 1 are added to get a sum of 0 plus a carrying of 1, therefore 10. Then you carry it to the next value. Then subtraction, you shall look at the rules of subtraction. And therefore, 0 minus 0 is 0. Then 1 minus 0 is 1. Then we have 0 minus 1. You carry 1. Therefore, you need to borrow, not actually carrying. You need to borrow 1 from the next figure. Then we have 1 minus 1 is 0. And therefore, let's look at this example here. We are doing it. 1 minus 0 is 1. But now, this one cannot be, 0 cannot subtract 1. Therefore, you take this one. And therefore, here it becomes 1 minus 1 is 0. Here you remain 0, but this becomes 10. And therefore, 10 minus 1 is 1. Because somebody else may argue it becomes 1 and therefore 0. No. When you bring this here, it becomes now 10. 10 minus 1, 1. Then this one remains 0. 0 minus 0, 0. Then 1 minus 1, 0. 1 minus 0, 1. And therefore, that's how you come up with that answer. Therefore, you need to practice and practice and practice. Then you can also look at this example here. That's 1 minus 0. So this one is just simple. It is just straight to the point. Therefore, practice, 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 make perfect. Then we can look at the subtracting using one's complement. Now, subtracting using one's complement, if you are told like 5 minus 3, the first step is to convert the 5 and convert the 3 into their binary equivalent. Then from there, you need to add them up and get the answer. Therefore, remember, computer usually perform subtraction by adding, and therefore, that's what we are doing. Therefore, if you are told to calculate 5 minus 3, the first step, you convert 5 to binary. You also convert 3 to binary. Then you add them up. In case you get an extra digit, we call it an overflow. And in one's complement, we add the overflow to the answer. In two's complement, we ignore the overflow. Therefore, example 2, we are subtracting 31 minus 17. And therefore, the first step is to convert 31 to binary and also convert 17 to binary. Then, since we are dealing with one's complement, you take the negative part. The 17, the negative part, you negate. You change the ones for 17. Like now, that one is this. 17 is this. Now, one's complement, when I was taking you through one's complement of a number, we have said one's complement of that number is negation of ones and zeros. And therefore, we shall only negate the negative part. That is 17. That's what we have done here. To convert this one to one's complement, you convert zeros and ones, and therefore this becomes 0, this becomes 1, this becomes 1, this becomes 1, this becomes 0. That is the one's complement. Then, once you do that, you now add the answer you got plus now the one for the positive side. Because now this one is now termed as positive, you add to this one. Then you get the answer. Now, the extra digit you get is called an overflow, and it should be added to the answer in one's complement. Then subtracting using 2's complement, the method is the same, only that in 2's complement, you get the 1's complement plus 1. That is the only difference. The other difference is that you ignore the overflow. And therefore, we are doing 27 minus 5. Therefore, the first step is to convert 27 to binary. You also convert 5 to binary. Then, the side with the negative, that is the 5, you do the 1's complement of it. That is the bitwise not. That is, you negate. You change zeros to 1's. Then, the answer you get, you add 1 to make it 2's complement. Then, the resulting answer, you now add to the 27 binary conversion. And in case you get an overflow, you ignore the overflow. Therefore, mark that in 2's complement, you ignore the overflow. You can also look at this example of 14 minus 7. The first step, you convert 14 to binary. The second step, you convert 7 to binary. Then, the one with the negative side, you get its bitwise not. You negate. You get its first, one's complement. Once you get its one's complement, because we are dealing with the 2's complement, 2's complement of a number is 1's complement of a number plus 1. Then the resulting answer, you add it to that one of 14. And therefore you can see this is the one for 14. This is the resulting answer for this negative part. Then you add. Once you get an overflow, you ignore. But in 1's complement, you add the overflow to the answer. Therefore, that is the end of our topic. Remember to subscribe if you have not subscribed. Also, remember I have done some other videos in elementary programming principles, system development, and data processing. Therefore, don't stop at this point. Continue with the other topics that is in Form 3. Therefore, thank you very much for watching. See you in the next video.